Well, good morning, everybody, and it's always a pleasure to be back here in Boulder, and I'm really excited to be part of this venture. Just to echo the words of Haley and the other organisers, we're really looking forward to hearing about your work and learning more from your insights as practitioners in a very broad field. I just wanted to say that I'm very fortunate to be working at Loughborough University. You can see it's a nice big green campus, probably the hardest place to spell and pronounce amongst all the places represented here. And I've really come full circle over the last 30 years. I showed up at this place in 1984 as an undergraduate, primarily motivated to try and get as close to a 4-minute mile as possible using the fantastic sports facilities here, and ended up also doing a fantastic geography degree at the same time. 30 years on, I think I've had a very checkered career history in the sense that I've held at least 10 posts as far as I can recall in the last 25 years. So you work out the average residency time. A lot of that is explained by my interest in working closely with decision makers and practitioners, and my career has been as much in academia as in industry, as in government, and even as a self-employed consultant for a time. So throughout the next 2.5 weeks, what you will be receiving from me is very much a pragmatic, practitioner-focused perspective drawn on this varied career history. I think I've been very fortunate to work in all sorts of exciting places around the world, but for me personally, the most rewarding aspect of the work that I do is when we are able to take this science, this insight, work alongside practitioners in some of the most water-stressed or problematic parts of the planet, and really see the extent to which our work can enhance human livelihoods and well-being. I've also obviously had a long history of scientific curiosity in the area of water research and uncertainty. And here's an example of some of my early work where, basically picking up on some of the points that Haley was making, I was curious about how much uncertainty is there in a hydrological model. And in some ways, hydrological models are far more tractable than a climate model to explore. In the worst case, we might just have 20 to 30 parameters to play with. But even so, we soon learn that the uncertainty attached to the very impact model, which is very late on in that top-down chain, can be immense in its own right. I was also, following that curiosity, thought, well, okay, let's try and open this out a little bit more and see how the uncertainty expands if we, for example, blend in a couple of emission scenarios, take 4 GCMs, that's all I had to hand at the time, a couple of downscaling methods, a couple of hydrological model structures, 100 plausible hydrological parameter sets, and we put that all into the blender and see how that shakes down in terms of projections for low flows in the River Thames, a very important point of water resource for London. And you can see in the bottom right-hand corner that once we blend these uncertainties together, we have this huge envelope of uncertainty, which is essentially plus or minus a very big number. And I guess it's from this early work that I came to the point that I concluded that this is intellectually challenging, it's scientifically justified, as already been pointed out, but in some ways we can begin by taking uncertainty as a given and then starting to think, okay, what can we do with this information? How can we work with it in smarter ways to assist decision makers? And that's really been the way in which much of my work has followed on from this type of analysis. I I've also, as I've mentioned, been very fortunate to work with a wide range of practitioners, mainly in government and agencies and in the donor world. So I've worked a lot in North Africa and the Middle East, in some very interesting and sometimes quite scary parts of the world. And that certainly focuses your mind as a scientist, trying to bring to bear your work in places of perhaps data scarcity, lack of technical capacity, and even the basics of a reliable power supply when you are trying to do research. And some of my more recent work with the new nuclear power build plan for the UK forces us to also think very far into the future. So if you take the anticipated time life of a new nuclear power plant being planned in the UK right now, it basically sums up to nearly 200 years by the time you've taken into account the design, the operation, the decommissioning, and the storage phases of that site. So here's a picture of one of our plants on the east coast of England. And what we're saying is we need to be able to design the platform height for a new nuclear power plant on that site that will be resilient to about 200 years of climate change. There are engineers grappling with that thorny issue right now, and that's clearly a really big technical challenge, one that has been addressed by others around the world, not least the Dutch, who have done some fantastic early thinking in terms of how we might adapt over those not multi-decadal but multi-centennial timescales. And frankly, when you're looking at 200 years into the future, we're almost at the point where the science and the science fiction are beginning to sort of meld. It's hard to tell them apart. And that's okay. We have to think about some quite exotic hazards if we're really serious about protecting the safety of a nuclear power plant and its spent fuel for 200 years. I thought it'd be interesting to introduce, again, perhaps a perspective through my preferred choice of top paper. Sorry, Casey, it's not yours, although you come a close second with your decision scaling paper, which I hope we'll hear more about this afternoon. But this paper I really love, by Stefan Hallegatte, because we've been asked to think about what do we know already? Well, we know that the future is uncertain. And as I mentioned before, Hallegatte begins with that assumption. The future is uncertain, but it's not an excuse for inaction. In fact, if we turn to the next slide, here's some work I've been doing with the World Bank in Tajikistan, thinking about the security of hydro energy supply in extraordinary situations of uncertainty. And here are the sort of half a dozen or so practical actions that Hallegatte envisages, and we can map real on-the-ground activities, including hazard forecasting, use of safety designs and allowances in the structure itself, even improving and strengthening monitoring and such like. So there's a huge amount of practical steps that we can take despite the uncertainty, and I think that's a really important premise to begin with. But the question is, how can we bring our science to bear to all of those activities on the right-hand side to improve forecasting, improve the robustness of those design standards? To me, that's where some of the really exciting research opportunities lie, and I hope we'll be unpacking some of these points later on. I also think it's there's a lot that we can do as a community to actually take our science, our research, and package it in ways that can be more accessible, more user-friendly to a very broad base of users and communities out there. And that's certainly characterized a lot of the work I've been doing over the last couple of decades, not least trying to bring together my research on downscaling into a tool that's freely available, and delivers information for impact studies at local scales. And those of you who keep watch on downscaling might be bemused by the latest version, which is actually GCM free. So you might be thinking, how can you have a downscaling model that doesn't require GCMs to run? And maybe more about that later. I've also worked quite a bit in Yemen, where there we're confronted by a whole host of logistical and technical challenges. And one recent project, we're helping to direct donors to target research and investments into climate resilience strengthening projects. So enhancing water collection, reducing soil loss, planning for changes in crops and crop management, all of these things. And we, again, packaged the insights from the modeling into these tools, put it into a Google world, and it enables the extension worker, the guy on the ground, to really examine the local context of that decision. And here we can see just one screen grab of one of the communities where it's being highlighted as a potential site for terrace rehabilitation, so to protect the slopes from soil erosion and flash flooding and such like. So although it looks simplistic at face value, there's a huge amount of science and analysis that goes on behind the scenes. And I mentioned also that data sparse areas, I think, present particular practical and scientific challenges in their own right. And if we're thinking in terms of flow forecasting, hazard forecasting in Central Asia, there are wonderful opportunities emerging from remotely sensed products combined with simple models on the ground that are appropriate to the range of uncertainty and the quality of the underlying data. And we can again bring together that information about the terrain, the remotely sensed information, the operation of some of the largest hydropower schemes in the planet to produce simple forecasting tools to aid decision making. I think also there are fantastic opportunities and great insights to be gained by working in country. And as I've mentioned before, I've worked Djibouti, Yemen, Central Asia, and many other places. And this again gives you a sense of what really matters in the uncertainty paradigm when we shake it all down. You know, where is the key emphasis we should place? Is it on the basic data collection, on the modeling, on the choice of climate model? You're really forced to confront some of the fundamentals when you're working in these kinds of environment. I think a number of the speakers already have highlighted the importance of observations, and just as a little sideline, about 3.5 years ago at Loughborough, we set up a long-term water temperature monitoring program to help track very high-resolution changes and responses to thermal properties of rivers in space and time. And we're now being able to link that to very peculiar changes in the ecology of these rivers. So much, again, can be learned from just some of the perhaps less elegant, less high profile, but routine monitoring. There's still a lot we can learn from that, so we shouldn't lose sight of it. Final point I'd like to make before coffee is there's this wonderful statement or phrase that emerged, I think, in the Economist a few months ago, about avoiding climate exceptionism. And this is really reminding us all that, yes, climate change is a key driver and a key concern, and the reason why many of us are here for these 2.5 weeks. But if you're unfortunate enough to be studying in Shanghai in a lecture theatre like this, why is it ankle deep in water? Climate change may be partly driving the changes in the frequency of heavy rainfall, intensity, duration, and the seasonality, but also the fact that the urban drainage systems there have been designed to withstand just a 1 in 6 month event. So you're accepting as a given that you're going to get wet at least twice a year in parts of Shanghai. So final remark is, yes, let's talk a lot about climate change, but let's see climate change in this much broader wrapper and context. Thank you very much.